Hello students, welcome back to the lecture. In the last lecture I have discussed about how to get the electronic states of a molecule. I will continue from the last lecture and then I will move to molecular spectroscopy, where I will see how the electronic orbitals of or electronic states of molecule is determined and how does a spectra of this molecule look like. So, in the last lecture what we did is we not only discussed how to get the spectra of atoms, we also started looking at application. So, two different kind of application we have already looked at. One is application of atomic spectroscopy in environment, and the second was the use in forensic science. So, continuing with the last lecture, now I am going to discuss what are the other applications of atomic spectroscopy. Atomic spectroscopy is quite often used in agriculture application. As we know that soil provides essential nutrients to the plants, and hence soil analysis provides a measure of soil's potential to supply the necessary nutrient to the plants. It is also well known that different kind of plants require different kind of essential nutrients, and so if you analyze soil, you will be able to tell which kind of crop is suitable to the kind of soil which a place has. Plants can also be sampled to monitor nutrient uptake efficiency and also to check the toxic metal accumulation for health reasons. So, what happens is that if toxic elements are present in the soil, that is taken up by the plant, and when you eat the plant's fruit or you use any product from the plants for eating purpose, that can have health problems, that can create problem in health. So, it is very important to analyze the soil to look at what are the contents available in the soil. Soils may become contaminated by the accumulation of heavy metals and metalloids through emission from the rapidly expanding industrial areas, mine tailings, disposal of high metal waste, leaded gasoline and paints. So, soil is always prone to be contaminated by the accumulation of toxic metals, which is mostly coming from the different industries. The heavy metals such as lead, chromium, zinc, cadmium, copper, iron and nickel are generally found at contaminated sites. So, these are the toxic metals, but some heavy metals such as copper, iron, nickel and zinc are required in a small quantity by organism. So, it is not true that metals are toxic only, some metals are required as an essential metal by organism. However, large concentration of these metals, which are useful metals, are also harmful to us, and so elemental analysis of soils is required. Now, next application is clinical applications. The majority of sample analyzed in the clinical sample are taken from the main group of biological fluids such as whole blood, plasma, serum and urine. Sometimes we also analyze hard and soft tissues such as bone, finger, nails and hair. Flame based analysis for the major and minor essential element, graph furnace analysis for the trace element and vapor analysis is done for the group of toxic metals. So, different kind of flame based analysis is done for different kind of metals. The tests are done for checking the quantity of several metals present in the blood sample. For example, some of the metals are essential, for example, calcium, magnesium, sodium and potassium. There are some minor elements which are also essential, for example, zinc, copper and iron. There are essential trace elements like chromium, manganese, molybdenum, cobalt, vanadium, selenium and nickel, whereas there are some toxic elements such as lead, mercury, arsenic, cadmium, aluminum and antimony. So, the essential major elements are required, and if the concentration of these metals are lower in our body, that can create problem. For example, if there is no iron, then a person is in anemic condition and a person is suffering from anemia. So, low concentration of iron is not good. Similarly, the high concentration of iron is also not useful. So, you need to have a balance of iron in our body, and if I want to know what is the amount of iron in our blood sample or our body, then we need to analyze these metal ions. So, here is list of some metal ion and their reference range in our body, and you can see this in the red. You have the toxic metals, for example, lead, its value should be less than 0.9 microgram per gram of blood. So, this is very important. If it is higher than that, then they are not good for us. Mercury should be less than 0.1 microgram per gram. So, these are the prescribed level, and our body should not have higher concentration of the particular toxic metal than the reference range. So, other toxic metals are arsenic, cobalt, and you can see for the iron, which is an essential element, the concentration range is 745 to 1050 microgram per gram. What does that mean is, you should not have iron less than 745, and you should not have iron greater than 1050 microgram per gram. If iron is less, then the person is suffering from anemia, and similarly higher iron content is also not good for our body. And since these are very essential element of our body, and so it is always required that you need to check the concentration of these metal ions in our body from time to time, and in that context your atomic absorption spectroscopy or spectroscopy based on your atomic spectroscopy is needed. Atomic spectroscopy has pharmaceutical application. It can be used for analysis of diclofenac sodium sample. Diclofenac sodium is a synthetic non-steroidal anti-inflammatory drug. This is a well known, most prescribed drug or highly prescribed drug, but there is a chances of this getting contaminated with the metal ion. The amount of metal and other contaminant present in the formulation of this drug should be followed as to minimize undesirable effect and should assure that bioavailability is not affected. So, sample of diclofenac sodium samples are analyzed for sodium, potassium, calcium and aluminum analysis. So, most of the formulation for drug are analyzed for your metal content, because the contaminants can have undesirable effect. Similarly, magnesium stearate sample is also analyzed for cadmium, nickel and lead. Apart from this, metals monitoring can be used as a fingerprint, either to control raw material quality used in the different pharmaceutical forms or to control the production process and the final product. So, these metals are not only analyzed for having undesirable effect, but also to check the quality of different pharmaceutical products. Here I am giving example of metals which is used in pharmaceutical. There is a long list of products where the analysis of metals is done for a particular biopharmaceutical or pharmaceutical product. For example, Prohance R, which is used as a imaging agent, and this is from Bracco Diagnostic Inc. The gadolinium is analyzed. Multi-Hans R, which is a imaging agent. This is also from Bracco Diagnostic Inc. and here what we analyze is again gadolinium. Fer Zinket R is used as imaging agent, and this is from Siner Med Limited. Here your analysis of iron is done. Venofer is an imaging agent, again it is from Siner Med Limited, and here again iron analysis is done. Dexferune R is from Vifor Pharma, and again here iron is involved, and so analysis of iron is being done. Lumen Hans R, it is an imaging agent from IMA RX Pharma Corporation, and here analysis of manganese is done. Tagitol R, it is an imaging agent, it is from Bracco Diagnostic Inc. Barium analysis is done. In Lithobid, which is used for schizophrenia, it is from Noven Therapeutics LLC, and here analysis of lithium is done. Gastrogafin R, it is an imaging agent from Bracco Diagnostic, and here analysis of sodium is done. Platinol, it is used in chemotherapy, it is from Bristol Myers Squibb company, and here analysis of platinum is done. The paraplatin, it is used in chemotherapy. It is from Bristol Myers Squibb company. Here analysis of platinum is done. Silvadene, it is an antimicrobial property, and it is from Monarch Pharmaceutical. Here analysis of silver is done. Ferroquine, it has anti-malarial property, and here analysis of iron is done. So, there is lot of pharmaceutical products where analysis of different metals are done. So, now we will go to another application. Metal analysis is quite often done in the petrochemical industry. Here what is done is our atomic absorption spectroscopy or atomic spectroscopy techniques are used to measure refinery contaminant elements such as sodium, vanadium, iron and nickel. Also, atomic spectroscopy used to measure fuel elements, lead, Mn, etc. It can also be used to measure the lube vial element. For example, in the fresh lube vial, the content of calcium, barium, magnesium, zinc, molybdenum and sodium is done to look at the quality of the lube vial. And in the used lube vial, the analysis of silver, aluminum, chromium, iron, manganese, nickel, lead, Sn, titanium, zinc are being done. That tells you about the quality or the degradation of lube vial, degradation of the lube vial. There are some other applications. For example, determination of traces of potassium in sodium chloride and sodium in potassium chloride, determination of alkaline and earth alkaline metals in electrolytes for infusion, trace elements in multivitamin formulations. So, multivitamin formulations has lot of trace elements, and it is important to analyze those trace elements. Similarly, atomic spectroscopy is used in aluminum assay in biological samples such as rat fodder or antacids. It is also used to look at zinc in insulin and cobalt in vitamin B12. Atomic spectroscopy is also used in the determination of lithium in antidepressives. Other applications include determination of silicon in dimethyl polysiloxane, copper determination in herbs such as Lupulli strobili, gold content of an organic gold compound used for the cure of chronic polyarthritis, determination of iron in diverse iron containing medicaments, determination of traces of lead in zinc oxide and zinc oxide formulations. So, there are several applications, and what I am listing is only few of them. For example, atomic spectroscopy is also used in zirconium determination in material used in dental medicine. Similarly, atomic spectroscopy is used to look at amount of mercury in pharmaceuticals, plant materials and herbs. It can also be used to look at the amount of thallium, cadmium and lead in herbs. Palladium is quite often used to synthesize drugs. So, the determination of traces of palladium in drugs is very important. Palladium is basically used as a catalyst for hydrogenation step during the manufacturing of drug. But when you purify your drug, then a small amount of palladium may be left, and therefore, it is required to look at traces of palladium in drugs. Potassium determination in urine, and this is basically done to look at bioavailability study of sustained release of potassium tablets. So, if you want to look at the bioavailability of any drug which has a metal ion, you can look at the amount of that metal in the urine sample. So, potassium can be determined in urine either after sufficient dilution at 766.5 nanometer or little or no dilution directly at 404.7 nanometers. So, just by looking at the absorption at different wavelength, you can know what is the concentration of potassium in urine sample. Okay, so during the last lecture, I only discussed the spectra of alkali metals and alkaline metals. What I left was a spectra of other polyelectron atoms. Since I did not have time that day, I could not talk about the spectra of other polyelectron atoms. So, here what I am going to do is, I will talk about selection rule for the atoms which have poly electron in outermost orbital. The selection rule is delta L is equal to 0 plus minus 1, except L is equal to 0 to L is equal to 0 is not allowed. For the promotion of only one electron, delta L is plus minus 1, that is what we know, but the general rule given here involves the total orbital angular momentum. So, we are talking here about total orbital angular momentum, quantum number L, and applies to the promotion of any number of electrons. So, it will be more than, it can be more than one electron. Now, one of the very important information about the selection rule for multi-electron atom is even to even, odd to odd is not allowed. Even to odd is allowed, or odd to even is allowed, but not even to even, not odd to odd. So, what I mean by even and odd? So, even and odd refers to arithmetic sum of sigma I L I over all the electrons, and this selection rule is called Laporte rule. So, what we need to do is, we need to calculate sigma L I, and if it comes out to be odd, then you tell that this is odd system, and if it comes out to be even, then you are dealing with even. So, what is the result of this? The transition of forbidden between states arising from the same configuration. So, same configuration, for example, suppose S2 we are talking about, or P2 we are talking about, then from P2 there can be different terms, but the transition between different terms of the same configuration is not allowed. For example, of the terms arising from 1s2, 2s2, 2p1, 3d1 configuration of carbon atom, 1p to 1d transition would be allowed if we consider only delta S and delta L selection rule, but Laporte rule forbids it. Laporte rule forbids the transition between states arising from the same configuration. Similarly, any transition between states arising from 1s2, 2s2, 2p1, 3d1 configuration, where sigma will be equal to 1 plus 2, 3, and those arising from 1s2, 2s2, 3d1, 4f1, where sigma Li will be your say 2 plus 3 5 are also forbidden, So, these are two important examples to understand what we mean by even to even is not allowed, odd to odd is not allowed, or even to odd is allowed or odd to even is allowed. Rule 3 is delta j should be 0 or plus minus 1, except that j is equal to 0 to j is equal to 0 is not allowed, and that I have discussed several times. So, I am not going to discuss in detail, and rule 4 is delta s is equal to 0. So, now we have looked at the transition between electronic states of different metal ions. We discussed about 3 different cases. One is hydrogen like atom, then we looked at alkali and alkaline metals, and now we have looked at the metals with more than one electron in outermost orbital. So, now we are done with atoms, spectra of atoms. Now, we will move to electronic spectroscopy of diatomic molecule. So, to get the energy state in the homonuclear diatomic molecule, we need to understand the molecular orbital theory. So, molecular orbital approach gives a fair qualitative description of electronic structure of diatomic and polyatomic molecule. So, here we will discuss only about qualitative part. In this approach, what we consider? We consider that two nuclei without their electrons are distance apart equal to equilibrium nuclear internuclear distance, and what we will do is to construct molecular orbitals around them. So, since it is diatomic molecules, so there will be two nucleus, and what we are going to do is we are going to assign atomic orbital to one and atomic orbital to second nucleus, and then we will construct molecular orbital around them. After molecular orbital construction, then we will fill electrons in the pair in order of increasing energy of orbitals to give ground configuration of the molecule. This the basis of constructing molecular orbital is known as linear combination of atomic orbitals, LCAO. So, here molecular orbital wave function is expressed as linear combination of atomic orbital wave function, which is chi I on both nuclei. So, your wave function for molecular orbital is given by sigma C I, which is the coefficient of wave function chi I, and chi I is wave function of atomic orbitals. So, if there are diatomic molecule, then there will be two terms here, two terms. There is a very important restriction for linear combination. For effective linear combination, three conditions should be satisfied. The energies of atomic orbitals must be comparable. The atomic orbitals should overlap as much as possible, and the atomic orbitals must have same symmetry property with respect to certain symmetry elements of the molecule. This is very important, and so you cannot go and take any atomic orbital and you make a molecular orbital. Energies of atomic orbital must be comparable. So, that is very important. So, suppose I have a homonuclear diatomic molecule, this is one atom, this is second atom. Then if I label this with 1 and the second atom with 2, then LCO methods give the molecular orbital wave function as psi is equal to C 1 chi 1 plus C 2 chi 2, where chi 1 is associated with the nucleus 1 and chi 2 is associated with nucleus 2. So, chi 1 is wave function associated with nucleus 1 and chi 2 is wave function associated with nucleus 2. Now, we can go ahead and calculate energy of molecular orbitals. So, energy will be given by S psi is equal to E psi, and if you multiply this by psi star and then you integrate it and divide this by psi star psi d tau, you are going to get energy. You are going to get energy, and this is well known variation theorem. So, combining the equation 2 and equation 4, so let us put psi at this place. When you plug in the value of psi, what you are going to get is this whole term. So, basically you are taking this star Hamiltonian multiplied by this psi d tau and you are integrating, and here you are integrating psi star psi d tau. So, what you are going to get is C 1 square chi 1 h chi 1 plus C 1 C 2 chi 1 h chi 2 plus C 1 C 2 chi 2 h chi 1 plus C 2 square chi 2 h chi 2 and d tau. And when you solve this, what you are going to get is C 1 square chi 1 square plus 2 C 1 C 2 chi 1 chi 2 plus C 2 square chi 2 square d tau. If the atomic orbitals wave function are normalized, then the chi 1 square d tau when it is integrated will be equal to chi 2 square d tau, and that will be equal to 1. And let us give a short notation for this H 1 2. H 1 2 is integral of chi 1 Hamiltonian chi 2 d tau, and then give a notation for this integral as S. If we do that, it is very simple to write this energy term, where energy will be C 1 square H 1 1, where H 1 1 will be chi 1 Hamiltonian chi 1 d tau with integral. So, if you remember here, you see here this is chi 1 h chi 1, and that is what we are writing as H 1 1. So, E will be C 1 square H 1 1 plus 2 C 1 C 2 H 1 2, since these two are equal. So, there will be twice of C 1 C 2 H 1 2 and then C 2 square H 2 2 divided by C 1 square plus 2 C 1 C 2 S plus C 2 square. Now, we can use variation principle to optimize C 1 and C 2 by putting d E by d C 1 and d E by d C 2 equal to 0. That is what we did when we were discussing the 2 electron system in an atom. So, if we do that, what we are going to get is this equation C 1 H 1 1 minus E plus C 2 H 1 2 minus E s is equal to 0, and the second equation will be C 1 H 1 2 minus E plus C 2 H 2 2 minus E s is equal to 0. So, these two equations we will get if we differentiate E with respect to C 1 and E with respect to C 2, and when we make it zeros, then we have two equations. These equations are called secular equations, and two value of E will be obtained if we can solve this. And the way we solve it is by writing a matrix where the matrix is 2 into 2 matrix. The first element is H 11 minus E, H 12 minus E s, H 12 minus E s and H 22 minus E s. Now, if you remember H 12, it involves wave function of both nuclei, and that is why H 12 is called resonance integral. Now, let us put it as beta, and H 11 H 22 is Coulomb integral, and they involve the individual nuclei, and put it as alpha. So, then circular determinants become alpha minus E, beta minus E s, beta minus E s, alpha minus E is equal to 0. And when you solve that, what you will get is alpha minus E square minus beta minus E s square is equal to 0. And if we solve this, we can get two values of E, which is known as E plus minus, and that will be equal to alpha plus minus beta divided by 1 plus minus s. If we assume that s is equal to 0, then we have E plus minus is equal to E a plus minus beta. So, same approximation we can write here. We have taken s is equal to 0. So, E s terms vanishes, and so what we get is these two equations. If we put the value of E plus and E minus, then we can get C 1 by C 2 is equal to either 1 or minus 1, and now we can write the two wave function corresponding to two molecular orbital. N plus n minus r normalization factor, which can be obtained from the condition this, and when you do that, what you will get is n plus is equal to n minus is equal to 2 minus r. So, this is your wave function. E we have already calculated, E is E a plus beta and E a minus beta, and difference between these two is 2 beta. So, two atomic orbitals on linear combination gives you two molecular orbital with energy E a plus beta and E a minus beta, E a minus beta. So, now we know that two atomic orbitals combine to give two molecular orbitals. Let us see and take orbitals one by one and see which kind of molecular orbitals we can get from different atomic orbitals. For example, if we take 2s orbital, then if they will combine to give you two molecular orbital, and one is your sigma g and this is sigma u star. This is bonding orbital, this is anti-bonding orbital. So, this is, and u is for ungerad and g is for gerad. So, 1s will combine to give you sigma u star 1s and sigma g 1s. Two atomic orbital or 2pz will combine to give sigma g 2p and sigma u star 2p, and 2px and 2py will combine to give pi 2p and pi g star 2p. Now, we can see that sigma will result from side to side overlap, whereas this pi will result from this kind of overlap, Now, we can write the molecular orbitals. So, in any atom you have 1s orbital, 2s orbital and this 2px, 2py, 2pz orbital. For the second one you have 1s, 2s, the 2px, 2py, 2pz orbital, and 1s is going to overlap with 1s and giving you sigma g 1s and sigma u star 1s. 2s orbital of one atom is going to combine with 2s orbital of another atom, giving sigma g 2s and sigma u star 2s, and this is the way your energy increases. So, lowest is sigma g 1s and sigma u star 1s. These are the different electronic states. different molecular orbital and their energies. Only difference comes in oxygen and fluorine, where the sigma g 2 p, this is sigma g 2 p and pi u 2 p, this one is reverse. It means that this will come down and this will come up. Otherwise, your this molecular orbital picture is valid for your any homo diatomic molecule. So, this is your different molecular orbitals and their energies. So, lowest is sigma g 1 s and then sigma u star 1 s, sigma g 2 s, sigma u star 2 s, and this is the way energy is increasing. For oxygen and F2 there is a difference at the last. So, you see here that till this point it is same, after that your sigma g 2 p and pi u 2 p there is exchange and again last two is same. So, this is the way your molecular orbital picture describes you the energy of different molecular orbitals. Now, let us think about your electronic states for diatomic molecules. Till now we have looked at what is the different molecular orbitals, how they differ in their energies. Now, we are going to look at electronic states. Vector L is strongly coupled to the electrostatic field. So, in the diatomic molecule, it is very important to remember a vector L is strongly coupled to the electrostatic field, and the consequently frequency of precision about the internuclear axis is so high that the magnitude of L is not defined. In other words, L is not a good quantum number for diatomic molecule. What we are going to look at is your orbital angular momentum along the internuclear axis, which is defined and which is equal to lambda h cross. This is lambda and h cross, where the quantum number lambda can take values 0, 1, 2, 3, 0, 1, 2, 3. So, look at this picture. Here we are not concerned about L, what we are concerned about is its component along the internuclear axis, and that is your lambda h cross, lambda h cross. Now, all the electronic states with lambda greater than 0 are doubly degenerate. Classically, this degeneracy can be thought of as being due to electrons orbiting clockwise or anti-clockwise around the internuclear axis, the energy being the same in both cases. The lambda is equal to 0, there is no orbiting motion and no degeneracy. So, lambda is equal to 0 does not have any degeneracy, but lambda is greater than 0 are doubly degenerate. Value of lambda like that of L in an atom indicated by main part of the symbol for an electronic state. So, if lambda is 0, it means you have a state sigma. If lambda is 1, corresponds to pi, lambda is 2, corresponds to phi, lambda is 3, corresponds to tau. So, that is what it is written here, that lambda 0 corresponds to sigma, 1 corresponds to pi, 2 corresponds to delta, 3 corresponds to phi, 4 corresponds to tau. Now, symbol for molecular orbital in linear molecule. Right now, we have looked at the molecular orbital, and what will be the lambda value, which is basically plus minus m, is for sigma this lambda is equal to 0, for pi this lambda is equal to 1, delta it is 2, phi 3 and this gamma 4. So, for example, if we are dealing with 1 sigma g 2, 1 sigma g 2, which is basically ground state of S2 atom. Now, you see there are 2 electrons in sigma, and so sigma lambda or sigma m will be equal to 0, and 0 corresponds to, if you look at, if lambda is equal to 0, it corresponds to sigma state, and that is what we are writing sigma, and G multiplied by G gives you G, and so it will have G rat symmetry. Now, look at the first excited state of hydrogen molecule, 1 sigma G 1 sigma u star, that is the molecular orbital. Again, if you look at the value of sigma, it is 0. So, value of lambda, it is 0 for sigma. So, this is 0, this is 0, 0 plus 0, and this is only thing changes is the symmetry. And so, these are the different electronic states associated with the particular configuration. So, sigma G is basically associated with your 1 sigma G 2, and this sigma u is associated with this excited state of hydrogen molecule. So, this is about L part. Now, what about S? Coupling of S to internuclear axis is caused not by electrostatic field. So, S is just opposite to L, which has no effect on it. So, electrostatic field does not have effect on S, but by the magnetic field along the axis due to orbital motion of the electron. Although electrostatic field does not have effect on S, we still have to look at component along this, because your S or LS coupling will be in this direction only, because L is in this direction. And so, component of S along internuclear axis is sigma H cross, and quantum number sigma is analogous to ms in an atom and can take value from S to minus S. What does that mean is, S remains a good quantum number, and for the state with lambda is greater than 0, there are two S plus 1 component corresponding to number of values that sigma can take, and that is we have already discussed in the atomic orbital, that if it can take two S plus 1 component. So, multiplicity of the state is the value of 2 S plus 1, as we have seen in atomic spectra, and is indicated as in atoms by a pre superscript, as for example, in 3 pi. If S is 1, then you have a 2 plus 1 3. Now, again go to hydrogen atom ground state, it is 1 sigma G 2, and since you have a sigma G 2, this can be like this. So, S is going to be 0, and so multiplicity will be going to be 1. So, since both can be occupied like this, so S is equal to 0 and multiplicity will be equal to 1. Now, take this case. So, in this case you have one electron here and one electron here, and now your multiplicity can be due to this or can be due to one up and another down. When both are on up, then your multiplicity is going to be 3, and when both are down, one is down and one is up, then your S is equal to 0 and multiplicity is going to be 1. Multiplicity is going to be 1. So, due to S you have two different energy states, whereas electronic states, where for 1 sigma G 2 there will be 1 electronic states. So, if we look at low lying electronic states of S 2, here we considered only the first molecular orbital or lowest energy molecular orbital and the first excited state. So, here you are going to have 3 different energy states. The ground state is 1 sigma G, and then you have a 3 sigma U and 1 sigma U. So, this is the electronic states of hydrogen atom. Other diatomic molecules, electronic configuration are retained by assigning electrons to a selected set of cells. Closed cells do not contribute to either the total spin quantum number S or length of the molecular term. The electronic configuration in which all cells are closed give only a single term. This is 1 sigma G. high spin multiplicity is possible only if there are open cells. Now, I will discuss only one case and then I will stop. For example, lithium 2, the ground state is equal to, in ground state there are 2 electron in sigma g, 2 electron in sigma u and 2 electron in 2 sigma g. So, all cells are closed. So, term symbol of ground state of lithium 2 is 1 sigma g. Now, let us look at one excited state of lithium 2. So, there are 2 electron in 1 sigma g, 2 electron in 1 sigma u star, 1 electron in 2 sigma g and 1 electron in 2 sigma u star. So, 1 electron from 2 sigma g goes to 2 sigma u star. Since both electron in open cell has m is equal to 0, this electron is in sigma. So, m is equal to 0. So, your lambda will be 0 and both s is equal to 0 and s is 1 is possible, because these are in 2 different states. So, it can be like this, it can be like this also. And so, s is equal to 1 here, in this case s is equal to 1, in this case s is equal to 0. And so, both s is equal to 0 and s 1 is equal to 1 is possible, and overall parity will be G cross U is equal to U. And so, you have 2 different terms, 1 sigma u and 3 sigma u. So, this is the way you can get electronic states of different states of lithium 2 plus lithium 2. So, we looked at in this lecture, we looked at how to get the different electronic states of your diatomic molecule, and once we know that, then using selection rule we can know what kind of spectra we can expect for a diatomic molecule. So, I will stop here and thank you for listening. Most of this material has been taken from, most of the material has been taken from modern spectroscopy book by Hollis. So, I will recommend this book to you. So, please go through it and try to understand. Thank you very much.